Okay, as I said, this is more for paper 5, question 1. Give you some ideas how to do the experiment in case it comes out. Right? This is the analog signal generator or power generator or oscillator or low voltage AC source. Use different waveform used in ripple tank experiment or force oscillation. Allow different frequency amplitude of sinusoidal waveform to be selected. Right? You can change the frequency of the alternating current or voltages. It's usually variation in voltage. And this is one of the experiment, right? Where there's a block of wood to investigate the resonance of mechanical system. So the vibrator will cause this spring are stretched. The vibrator will cause the spring to vibrate and the mass to vibrate up and down. And then you can observe the amplitude by observing the marker. Marker can be a pin attached to the bottom of the piece of wood. And then you can study the damping effect on the amplitude, right? By increasing the cardboard, increase the amount of damping. Okay. So usually you have to identify the parameters, frequency, amplitude of vibration, amount of damping. Then you have to write down the procedure. Set the frequency of the vibrator and note the amplitude by reading the marker at the base of the mass. Repeat with various frequencies, note the frequency amplitude, and each time employ a graph of amplitude against frequency. To increase the amount of damping, place a manila cut against the bottom of the mass, perpendicular to the direction of vibration. Cross-section area of the cut determines the amount of damping. Okay, the other experiment, this one is came out in November 2006. I don't know whether your teacher allowed you to do or not. Just a wire attached to a mass there, and you have two magnets facing each other. And all you need to do is adjust this plug or crocodile clip up and down until you see a big vibration. And you use alternating current. Then you can measure the length. When the current flows through the wire, it experiences a force either into the slide or out of the slide, depending on the direction of current flow as given by Fleming's left-hand rule. When the current goes down, goes up, so that will cause the wire to vibrate using Fleming's left-hand rule. When the direction of current changes, the direction of force changes. When the alternating current is used, the wire is forced to oscillate, adjusting the oscillating length. L adjusts the natural frequency for forming the standing wave of the loop. Right? That's the length. So it will oscillate with large amplitude where it has reached the natural frequency of the wire, natural frequency of oscillation of the wire. Okay. Usually they will give you a formula Then may not be that nicely done right? The tension is related to the length as for F square L square M. When the frequency of the alternating current source and mass is and M is the mass per unit length of the wire. In the experiment, we will investigate how the length of the vibrating wire is affected by tension in the wire. Right? So usually they will guide you what are the things they want Independent variable, what you change Dependent variable, what is responding and what is kept constant. Measurements, how would you determine the length, extension, and diameter of the wire? Analysis, what graph you would plot to obtain a straight line graph? How would you determine the frequency of the alternating source? Okay, so you want to investigate how the length of vibrating wire is affected by tension in the wire to determine the mass per unit length of the wire. Right? Investigate how the length of the vibrating is affected by. Right? This is the formula that is given. So I have to rewrite the formula as this formula. Then independent variable is T, tension. Dependent variable is the length. M and F from the equation, you have to keep your F constant. You have to keep the Y, use the same wire. Right? Keep F constant. And how do you determine T? T is mg. Mass measure using electronic balance or top band balance. And plot a graph of L square against T. A straight line passing through the origin. There's the gradient. Right? F is determined using CRO. How determine it? You determine the period using CRO. And F is one of the period. Right? L can be measured using meter rule or half meter rule. So you should be able to get 7 marks. So you can do all that out of 50 marks. Right? This is Bolton's pendulum. This is a driver. And this the cone is give you the amount of damping. So illustrate resonance. These two will oscillate together. The others will oscillate out of phase. Okay, so let's just draw on a piece of paper or PowerPoint. What are the things you have learned? No? X X and V are half radian out of phase. X and A acceleration and displacement are pi radian out of phase. Amplitude, maximum displacement on the rest position, that's amplitude. Omega is angular frequency, frequency expressed in radian per second. And period of an oscillation is the time to complete one oscillation. Frequency is the oscillation in number of complete oscillation per unit time. So summarize all this. Okay, this is my own mind map. You can draw your own to summarize. It will help you. Okay, we have completed this topic. Let's go to do some question. Okay, let's try number 11. A student sets out to investigate the oscillation of a mass suspended from the free end of a spring, as illustrated in the figure. The mass is pulled downwards and then released, and the variation with time of the mass of the y of the mass is shown in figure 3.2. Use the information in 3.2 to explain why the graph suggests the oscillation is undamped. Okay, why does the graph suggest that the oscillation is undamped?
Same as you.
Constant amplitude, good. Amplitude of oscillation is constant. Answer the following question. We are using the same graph. Say 2 times where the velocity is maximum in the same direction? Can from the graph?
Uh,
This is applying your AS work. Velocity is your gradient, no? Right? Gradient. So you take here, then the other one is here. No? The one is here. No? Here one there is about 0.93. Or if you take this one, 0.55, then the other one is here. No? Right? Negative gradient, negative.
oh, okay.
Stay two
There's a
times.
lot of,
Say again.
there's a lot, right?
Can't hear what you're saying.
There's a lot of instances.
A lot of places, not only these two. Right? If
Oh,
you
yeah.
take this one, then the other one is here, the other one is here, the other one is that part there. No? Okay. Stay
Yeah.
two times where the acceleration is maximum and in the same direction.
Um,
Remember your acceleration and displacement are pi radian out of phase. So you just label
0.35.
0 and 0.75, or
Uh,
can be also 1.5, or 0.35, you are right, 0.35 here, and 1.15, 1.1 second, or 1.85 second. No? Sketch the potential energy time graph of the motion. Can sketch. Right? Use the spring to help you. Right? Half ky square. Okay, let me just right? Half ky square. Just draw that. No? Okay, you square that. Negative becomes positive. You square that. Becomes
yeah.
right? Negative becomes positive. But remember, this is sinusoidal, so not sharp. Not sharp. Right? Sinusoidal. Right? Like something like that. Lah. Right? Like this is a displacement time graph. And then this one is a potential energy. Lah. Okay, let's carry on. Calculate the angular frequency of oscillation. Can
What a formula. Yeah. Okay. 2 by F.
F or 2 pi over T lor. Right? 2 pi over T. T is 0.5 second. That's your, from here to here is the period. Determine the maximum speed of the oscillating mass. How to do that? Maximum speed. Remember your circular motion, no? V naught times R omega, no? Okay? Or
Yeah.
use gradient, no? Another way is to use gradient. Determine the resonant frequency of the mass spring system. And from here, no? From here, or from the period. Okay?
Oh, okay. Yeah.
Any comments so far? Or anything not
No.
clear? The student finds that if short impulsive forces of frequency half F naught are, are impressed on the mass spring system, a large amplitude of oscillations obtained. Explain this observation. It means he push and then he
Surface area, is it?
no surface area resonance also at half F naught. Pulse provide to the mass and alternate or some oscillation build up the amplitude. Right? It's just a resonance. That's why you push, you miss, you push, you miss, you push, you miss. No? Okay. So you build up the amplitude. No? The energy is given by the force or by the external force or impulsive force. Can
Yeah.
okay, see whether you can remember simple harmonic motion.
Simple harmonic motion.
Is memory work. Or acceleration is proportional to displacement from fixed point and direct towards the fixed point. A horizontal plate is vibrating vertically as shown in figure 3.1. Right, that's a figure. The plate undergoes simple harmonic motion with a frequency 4.5 Hz and amplitude 3.0 millimeter. A metal cube of that's a metal cube of 5.8 gram rests on the plate. Calculate for the cube the energy of oscillation. How to do it? What should I do?
Uh, 1/2 kx squared.
How to find K?
Using the formula. Wait, let me see.
Calculate step by step. Oh. Energy is
Mm.
half mr omega square, half mv square, right? V naught. V naught is r omega. Oh. Then omega is 2 pi f. Oh. And substitute your value inside there. Oh. Can. Right? Omega is
The angular velocity.
2 pi, f is 4.5. Okay, not? Just remember half
Everything
mv
using
square.
angular velocity.
Remember it's half mv square. Then replace the v with r omega no? Or x naught omega. No? This is the total energy. Okay, now. Then omega is 2 pi f. No? Which part is not clear?
Clear.
Right? I have to convert the gram to kilogram. That's the mass. And then amplitude. Amplitude is right? 3. I change to meter. Right? I square that. Then omega is 2 pi. 2 pi. F is 4.5. The whole thing square. Okay,
Yeah.
Amplitude of the plate in B is gradually increased. The frequency remains constant. At one particular amplitude, the cube just loses contact with the momentarily with the plate. State the position of the plate in its oscillation at the point where the cube loses contact. Yep.
Well, what does it mean by state of position?
Let's just set up the plate, the cube going up and down.
Okay.
State the position of the plate in its oscillation at the point where the cube loses contact. Remember, the plate is oscillating in simple harmonic motion, whereas the plate is only causing the cube to vibrate, but there are certain time where they lose contact, where the plate is moving at a greater acceleration
Down.
than the cube. The cube is falling at acceleration due to gravity. Can
Hmm.
where
Does it mean like
at maximum displacement above the rest position, no? At maximum
above
position,
the rest position?
the
Means going up
acceleration
that
is the
time?
greatest. Acceleration is the greatest, greater than 9.81. So the plate will move down faster than the cube. Then the cube will catch up because acceleration now start to decrease. Okay now,
Hmm.
calculate the amplitude of the oscillation. How to do that? Right? Use a definition for SHM. Right? Where G is 9.81 and then acceleration is 9.81 and 2 pi, right? Omega is 2 pi f, frequency is 4.5 and then x naught. Calculate. Can.
Yeah.
That's where it start to lose contact. Okay, I don't think we will do this one because we haven't done we've done electromagnetic induction yet. Anyway, I will just record down lah. Right? State
Mhm.
evidence. Maybe we can try lah. See whether you can understand or not. A bar magnet is suspended from a free end of a elliptical spring as illustrated in figure 3.1. The elliptical spring, there's your magnet, there's your coil. One pole of the magnet is situated in the coil of wire. The coil is connected in series with a switch. That's a switch. There's a resistor. The switch is open. The magnet is displaced vertically and then released. As the magnet passes through the rest position, the timer is started. The variation with time t of the displacement y of the magnet in the rest position is shown in figure 3.2. Okay, so that's the picture. At 4.0, the switch is closed. So when the switch is closed, let's just review that. When the switch is closed, as this one oscillates, it induces current in the circuit. So it means that the energy of the oscillating magnet is converted into electrical energy, as loss and loss as heat. So that's why the amplitude start to decrease. State the evidence for the magnet to be undergoing free oscillation during the period 0 to 4 seconds. Yep. State the evidence for the magnet to be undergoing free oscillation during the period t equals 0 to t equals 4 seconds. Can?
Evidence meaning like different amplitude. I mean, same amplitude
This
constant.
one is free oscillation. Free oscillation means amplitude is constant.
Oh yeah, constant.
Okay, now amplitude of
Mm.
oscillation remains constant. That's the before the 4 second there. Yeah, 4 second there, all the amplitude are constant. So free oscillation. State a reason whether the damping after 4.0 second is light, critical, or heavy.
Light.
Light, good.
Eh?
Light,
Uh-huh.
after 4 second, amplitude oscillation decreases gradually, so it's light damping. Determine the natural frequency. Okay, you got 10 more minutes. Determine the natural frequency of vibration of the magnet on the spring. How to do that? Yeah, that's your graph.
By looking at the graph,
How? First, what do you determine?
determine the amplitude. Looking at the amplitude.
Huh?
Wait.
Determine the natural frequency of vibration of the magnet. So you determine the period first, okay or not?
Oh
Then from there
yeah,
you get the
yeah.
natural frequency, 1/t is the frequency. This one we haven't done yet, so no point. This one memory work only. Induced EMF is proportional to the rate of change in magnetic flux linkage to the circuit. Every year, simple harmonic motion will come out one. Every year, gravitation will come out one. Okay?
Hmm.
And one topic on heat. Explain why after 4.0 seconds, the amplitude of vibration of the magnet is seen to decrease.
Because of light damping.
What causes a light damping?
Uh, lesser driver force, lesser driving force.
You have to relate to the magnet. Current is
Oh,
induced in the coil as the magnet moves in the coil. Current in the resistor gives rise to heating effect. This thermal energy is derived from the energy of oscillation of the magnet. Thus, mechanical energy of oscillation decreases. Right? So the oscillating magnet has mechanical energy. When it's damped, current flowing through the coil and the resistor, energy is lost. So the mechanical energy is converted into electrical energy and finally converted into heat. So that's why you have damping, no? Amplitude decreases, no? Okay or not?
hmm.
Summarize, no? What is resonance? What is free oscillation? What is forced oscillation? What is resonance? And then the graph. Anything to ask?
So far no.
We still got 7 minutes, so we can start on electric field.
Okay.
Right? Topic 18, 19, 21. 21 is basically a combination of magnetic field and alternating current. So electricity and magnetism. Right? According to syllabus, under electric field, we will go to electric field and field lines, uniform electric field, force between point charges, electric field of point charge of a point charge, electric potential. Right? Don't bother the reference, you can use your own textbook. Right? What is given? You will use 9.81 and then this formula, permittivity of free space, you can get from the data sheet. And then potential is given, potential energy is given. Now where to find it? Okay, this one is basically, that's your syllabus. Usually, this one was in the old syllabus under AS. Now they remove it to A2. Page 109, type of charges, electron, negative charge in the electron cloud. Right? Find electron in the negative cloud of the atom. Proton and neutron, you can find the nucleus. Proton is positively charged, neutron is neutral. Particle find the nucleus. Neutral atom, number of electrons equals number of protons. Ionization, electrons may be removed from neutral atom, leaving the atom now an ion with a negative positive charge. Atoms may acquire excess electron and become negatively charged. So if you lose electron, it becomes positively charged. If you gain an electron, the atom becomes negatively charged. Contact forces, action at a point. Right? Friction is action at a point. This is your block, this is your table. Right? There's your load or the weight. And this is your apply force. Forces act when bodies are in contact. Just like here. The body pulling on the string, contact force, action at a point, you produce tension. Example would be friction and tension. If the block doesn't touch the table, there's no friction. If the block doesn't tie to the string, there's no tension. Right? Action at a distance compared to action at a point, action at a distance. Electric force is action at a distance. It doesn't have to be in contact. These two, one positive charge, one negative charge, balloon will attract each other. Object experience a force when they are a distance from the other object. Electric force is an action at a distant force. A charged balloon can have an attractive effect upon an oppositely charged balloon even when they are not in contact. Right? They don't have to be in contact. A positive charged balloon will attract a negative charged balloon. Right? Negative charge will attract a positive charged balloon. So we say electric force act over distance separating the two objects. You can show it there as a charged balloon. We blow it down. Right? Looks like there's a charge there pushing, it becomes greater and greater. The diffraction is become greater. Consider a physics demonstration in which a charged object is brought near the plate of a needle electroscope. Prior to any contact between the electroscope plate and the charged object, the needle of the electroscope begins to deflect. Right? They don't have to touch. As you come nearer, the charge is greater, the deflection is greater. The charged object exerts an influence upon the charged electrons in the electroscope even though physical contact is not made. The charged object affects other charged objects which were in the surrounding neighborhood. Around the charged object is an electric electric force. Right? We say there's an electric field there. Right? That's why it influences the electroscope. Okay, like charges repel, opposite charges attract. Electrons may be removed from a neutral atom, leaving the atom called ion, which is a net positive charge. Atoms may also acquire excess electrons and become negatively charged ions. What is a force field? A force field is a space or region, memorize where a force is experienced by a particle placed in the field. Example, electric force is a force in an electric field. So that is your region. If it's electric field, you put a charge there, it experiences a force. That's what it means by a force field. Particle experience a force. Charge creates an electric field around itself. The region of field is infinite. An alteration of space in the region we surround it. You can represent the field by field lines or line of force. How can we show the line of force and measure its strength? What is meant by isolated charge? An isolated point charge is the only charge in space and no other